I was getting a bit puzzled there. I just simply made a mistake. I put a 1 here before, it should be 2, but I had a 1 here and it was actually working, but that was incorrect. So I should have put a 2 here. Now, so when I do have a 2 here, you get 2m, the n's cancel, so this is 5, so m is 5 over 2. Now that is not an integer, so that can't be true. So either way, m is not an integer that way, or m is not an integer this way. So it can't be done. You've got a contradiction, right? So the contradiction is that m is not an integer, but the specification was that m and n are both positive integers. So if this is true, then you deduce that m and n, or m at least, is not an integer. So by RAA, by proof by contradiction, you have shown that you can't have m and n both integers such that this is true. Okay, so that's that one. Right. Next example. Prove that a number, so an integer, plus its square is always even. Now that shouldn't be too hard. So let's so you take a number, an integer, you add to it its square, and you have to prove that it is always even. Okay, so so n belongs to the integers, and you have to prove that n plus its square, n squared, is even. Okay, so how would you do that? Well, now it's the same number, right? You're using the same number. Now it's an integer. Now there are only two cases with integers. They're either odd or even. So if they're even, let's do the two cases. If n is even, then n takes the form of, say, 2p, where p's an integer. So therefore n plus n squared is 2p plus 2p squared. Right? So that's 2p plus 4p squared. And you take the 2 outside, so you're left with p plus 2p squared. Okay? And whatever this is, you multiply it by 2, so it's even. So that's even. Right? Now that's one case. Now what about when n is odd? Well, therefore it can be written in this form, 2q plus 1. Right? So let's plug that in. So therefore n plus n squared will be of the form 2q plus 1 plus 2q plus 1 squared. So it's 2q plus 1 plus 4q squared plus 4q plus 1. So that's 4q squared plus 6q, these two, 6q plus 2, right? 1 and 1. So, okay. Now you have a factor of 2 in common, so 2q squared plus 3q plus 1. Now whatever this is, you're multiplying by 2, therefore this whole thing must be even. Alright? So when n is even, the number plus its square is even. Show that here. When n is odd, a number plus its square is also even. Okay. Now they're the only two cases. So you've proved it's true for all cases. There are only two of them. And you've shown that it's true, therefore it's true in general. Right? That's the nature of proof. You have to prove that it's true for all cases. So we've done that. Right? So that's that proof completed. All right. Here's if x is a real number, I'll write that in a different way. Introduce to you a new symbol if you've not seen it before, which you probably have. Okay, so if x is less than 1, now x, by the way, belongs to R, big R. What does that mean? Big R, capital R, is the usual symbol representing the set of all real numbers. Okay, so if x is less than 1, then x squared is less than 1. Right? That's your p if p then q. So that's your p and that's your q. Right? So prove that. If p then q, so if x, which is a real, so if x is less than 1, then x squared is less than 1. Prove that. Or disprove it. Okay? So, which way are you going to go? You're going to try to prove it, or you're going to try to disprove it? Now, to disprove something, remember, you only have to find one counterexample. That's enough, that's sufficient to kill your hypothesis, to kill your assertion, your conjecture. Well, let's see if we can find one counterexample. Can you think of something? Think of some real number x that's less than 1, such that x squared is not less than 1. Can you think of something like that? Well, try this one. Let x equal -2. Right? So -2 is obviously less than 1. Okay, so that's true. But x squared, that's -2 squared, that's 4, right? But 4 is larger than 1. Okay, so we've found an x, -2, where this is not true. So we've found a counterexample. So so q is not true. So this is false. Right? So we proved that it's not true. All right. Another one. Prove if the square root of a plus b equals the square root of a plus the square root of b, if that's true, and then that implies that a is naught or b is naught. So how would you go about doing that? Okay, so this equals that, and you have to prove that either a is naught or b is naught. So root of a plus b equals root a plus root b. Well, what would you do? What would your next step be? Well, I guess square both sides. So the square of this equals the square of that. So if you square that, you just get a plus b. You square this, you'll get a plus root ab plus b. So these cancel. So you're left with root ab equals naught. Right? So that implies either a is naught or b is naught, or both.